Hey everyone, Mr. Fransky here. Today we're going to be talking about the intro to 5.1, which is estimating with finite sums. And it's really just an introduction to what we're going to be talking about for all of Chapter 5, which is finding area underneath a graph. But today we're just going to look at how we can do it using some finite values. So we're going to be doing a little bit of geometry today. And it's really not too bad, but this introduces kind of a topic that we talk about really for the rest of the year. So, wait, that's important. Let's see what's going on here. So I'm driving 65 miles per hour on 35W from 8 to 10 o'clock. So assume that 8 o'clock is t equals 0. What we're going to do here is graph the velocity and see how far I went. So the idea of how far I went, maybe we can't quite do yet, but as far as graphing the velocity, so this is going to be a pretty boring velocity graph, right? You can try this on your own if you want to pause the video, but I'm just going to graph here. So here's our velocity, v of t. Our time axis here. So we say 8 o'clock is t equals 0. So from 8 o'clock to 10 o'clock, I'm driving 65 miles an hour. So what's that graph going to look like? Well, here's 65, and here's what I'm doing. Okay, so here's 1, and here's 2. Okay, so here's 0, so 8 o'clock, 9 o'clock, 10 o'clock, right? So that's it. I drive at 65 miles an hour on 35W from 8 to 10. That's it. So the question of how far I went, well, for those of you that are taking physics, you can figure this out pretty fast, right? I went 65 miles per hour for 2 hours. You can even just think about it in terms of dimensional analysis. 65 miles per hour multiplied by 2 hours. The hours cancel. You end up getting 65 times 2 is 130 miles. Okay. Now, the question is, how far did I go? Well, 130 miles. And then the next question is, how is that number represented geometrically on the graph? So from this graph, from this velocity graph, if I multiply 65 by 2, what have I done? Well, I've multiplied the y value up here, right? The height here at 65. I multiplied by the x value, which is 2 down here. So what did I find? I found the area of this rectangle. Okay? So this is the first time we've really talked about finding area on a graph. But this is the area between what I'm going to call here is my velocity graph. Okay, so between the graph and the axis, right? So all I really want you to get from this bell work is that finding this area is somehow important. Okay, so area is somehow important. Because really, you probably never thought about finding the area between like the x-axis in a graph before, but somehow this is going to be important to what we're going to be talking about for really the rest of the year. So what if my velocity is changing, right? Because often you're not like driving at a constant speed the entire time. It might be changing velocity. So the question is, does it still work? Well, let's think about it. What if we had a velocity graph like this? So let's say that you're increasing your velocity linearly. Okay, so let's say you're increasing your speed up to 60 miles per hour. No one would ever do this, right? Start at 0 and you're like a slow crawl for maybe, I don't know, 2 hours again. Sure. So for 2 hours, you're taking that entire 2 hours to crawl slowly up to a speed of 60 miles per hour. So my question is, at the beginning, like from 0 to like 0.5, do you drive as far as you do from 0.5 to 1? Well, no, because you're going slower at the beginning, right? So if you're going slower for a certain amount of time, you're going to not cover as much distance. So this makes sense to me that the area here, the area of this little triangle is going to represent how far I move in that first half hour. Another thing to think about is like units up here are in miles per hour. Time is in hours. So it makes sense to me that multiplying the velocity by the time should cancel out those hours, and it's going to give you those miles, right? So multiplying the length along your y value, I should say, multiplied by the x distance should give you the change in distance here. So again, we're just trying to kind of figure out why this is important and how this area is important to what we're going to be doing. But in this case, if I wanted to actually find the area here to find the distance, yeah, the area, I can just use a triangle, right? It's just geometry. So the area here, the distance traveled is going to be 1/2 times base times height, so 1/2 times 2 times 60. So 1/2 times 2 is 1 times 60 is 60 miles. Okay, so if you spend 2 hours driving slowly up to 60 miles per hour, you're going to end up driving a total of 60 miles. Cool. So sometimes graphs don't even look this nice, right? Like sometimes they're even worse. So it could be like a parabola. Okay, so if we have a parabola like this, and let's say I'm still accelerating to 60 miles per hour in 2 hours, let's say. So the question is, well, I don't know how to find this area, right? I'm trying to find the area between the curve and the axis. That would be the exact distance that I've gone in those 2 hours. But I don't really have a way to do that. So today we're gonna talk about how we can approximate. So how can we get close to that value? Okay. And the question is, well, what shapes are easy to find the area of? Triangles are really easy, right? Rectangles are also really easy. So today we're going to kind of focus on rectangles. Rectangles are easy to find area, right? And if so we can find the area of rectangles, why not break this up into a few different pieces of rectangles, right? So we have this parabola. So what we could do is we could use what's called a right side rectangle method. I'll kind of describe that in a second. What you do is you make a bunch of rectangles where the right side, right? So this is the right-hand side of each one of these rectangles. Right-hand side is the thing that goes up and meets the curve, right? So maybe I can use some technology here and use some different colors. Okay, so what I'm doing, the reason it's called the right-hand side rectangle method is because the right-hand side is the part that I use to actually find the value from the function, right? So the right-hand side of each of these rectangles is going to run up to the function. Now what I'm going to do is find the area of each one of those rectangles. And you can see here, is that area, is it going to be too much or not enough? Looks like it's going to be too much, right? I have this compensation on the top of the curve. This is going to be way more than the actual distance traveled, right? But it's going to be a decent approximation. It's not going to be a terrible approximation. So there are 3 different rectangle methods that we're going to use today. We're going to learn about. Let's talk about these. So there are 3 different ones. So the first is called RRAM. That's the one we just looked at. It's the right side Riemann approximation method. Riemann is the name of a guy that had a lot of influence in the calculus world significantly later than Leibniz and Newton. The right side Riemann approximation method. And he specifically developed these kind of ways to approximate the area under a curve. Sometimes because not a lot of people are familiar with Riemann, people just substitute it for. Okay, so RRAM, right side rectangle approximation method. So to do that, if you have any function, looks something like this maybe. What you do is you divide it into any number of intervals. Sometimes they tell you to use even intervals. Sometimes they give you a table or something and the intervals are not even. But what you're going to do is you're going to run the right side of each interval up to the curve. Okay, so the right side of each rectangle up to the curve. And that is going to determine an approximate area underneath the curve, right? It's not going to be great, but it'll be okay. Notice some of these are on top, some of them are underneath. We'll talk about that in a second. Okay, so some of them on top, some of them underneath. But RRAM just basically using the right side of each one of these intervals to be able to go up to the graph and then figure out what that height is. Okay. So to find that, really, it's just f of x. So we have an x here. This height right here would be f of x. We kind of talked about that a little bit when we were talking about optimization. Okay. So RRAM's right side, what do you think LRAM is? LRAM is left side. Okay, so left side rectangular approximation method. So if we have a graph, I don't know, maybe it's a semicircle. Okay. So left side means if you partition it into subintervals again, and I use the left side of each one. We'll come back to the beginning in a second here, but like for this region, I would use the left side. Looks something like that. This guy looks something like that. Something like that. Over here, left side like that. Left side like that. Now this first one, what would the height of this first one be? Well, the left side is 0, so it wouldn't have any height at all, right? So if I was to find these areas, these rectangles, it would just be. And so again, some of them on top, some of them underneath. As long as we're talking about the over-under estimate, well, we'll get to that in a second, I guess. The last one we have is called MRAM. MRAM is the midpoint. Okay, midpoint rectangle approximation method. Because as you can see, like right side sometimes is too high, sometimes it's too low, left side, same deal. But if you use the midpoint, there's a chance that the midpoint will be a better approximation. So then we go back to our kind of parabola here. Okay, so if we partition it off like this, okay, so what you're going to do is you're going to use the midpoint of each one of those. Okay, so the midpoint is going to run up to the curve. We make a rectangle out of each one. So each interval we use the midpoint. So you see, it kind of goes on top and below for each one, right? And depending on the function, some of these are better than others. Sometimes, like if they change the curve like this, then maybe using left or right side will be okay because like half of it will kind of make up for the other half. Midpoint is often the one that's actually closest to the actual area under the curve, but it just kind of depends on the way the curve is shaped. Speaking of which, actually, before I do that, let's go back and let's kind of talk through actually finding this. So if we have this exact rectangle, or this exact parabola, so we have the point 260 here. I'm trying to think how I could actually make a parabola like this. So it'd be some kind of ax squared. So it'd be like, let's see, if ax squared is equal to 60 when x is 2, then a would be 15. So this curve could be 15x squared. Okay. This curve could be 15x squared. So if I'm going to try to find the area here using the right side Riemann approximation, the height of each one of these is going to be determined by the function. So if we have 4 rectangles here, that means that we're using 0.5, 1, 1.5, and 2. So 0.5, 1, 1.5, and 2. And if I want to actually plug these in, so the area of this first rectangle, would be base times height. So it'd be 0.5 times 15 times 5 squared. That'd be the area of that first rectangle right here. The next would be 0.5. Notice the width of each one of these is 0.5 times the right side run up to the curve. Right side is going to be 1 squared times 15, so 15 times 1 squared. The next one's going to be 0.5 times 15 times 1.5 squared. And the next one's going to be 0.5 times 15 times 2 squared. Well, you can grab a calculator, plug these in, or you can try to do it by hand. You can pull a 0.5 out to the front. 0.5 times, then we'd have 15. 0.5 squared is 1.5. Is that right? No, 0.25. So 15 times 0.25, that's 15 quarters. The next one, I pull out the 0.5, so we have 15 times 1, which is 15. The next one would be 15 times 1.5 squared. 1.5 squared is 2.25, so 15 times 2.5. And then we know this one, 2 squared is 4 times 15 is 60. That's why we chose that, right? And that should be the top value of 60, which makes sense. Again, you could do this by hand. Quarter of 15, right? 2 and a quarter of 15 here. Add them all together, you get a fraction or a decimal, something like that. But again, this is going to be too much, right? If you do a left side, the first one will be nothing. The next one will be like that. Next one will be like that. So it takes a little bit of practice, but eventually you'll be able to graph these this quickly as well. So notice this time we miss a bunch, right? So left side is missing a whole bunch of them. This would actually be an underestimate. Let's talk about that. When it's going to be over, when it's going to be under. AP likes to ask this question. So first of all, are there any hypotheses? So we've talked about over and under estimates once before. It was when we were talking about linearization, right? And we had the tangent line that was either on top or underneath a graph. Remember that depended on concavity, right? So generally, whenever you hear over or underestimate, there are kind of two things you have to take into account. One is the concavity, but in this case, the concavity is actually not going to be what determines whether it's an over or underestimate. Concavity determines over or underestimate for linearization and also for something else we're going to talk about later in chapter 5. But in this case, the way to figure this out is to draw things that are increasing and decreasing. So f prime positive, f prime negative, and then concave up and concave down. Okay, so it's important to be able to fill in this chart, and I do it often because I always forget how to make sure things are over underestimates, but it's always either depending on increasing, decreasing, or concavity. So it's either concavity or it's increasing, decreasing. We have to figure out one of these. Okay, so something increasing concave up would be like e to the x, so it would look like this. Something increasing concave down would be like natural log x, like that. Something decreasing concave up would be like e to the negative x. And something decreasing concave down would look something like that. So maybe like negative natural log of x or something like that. Okay. So now what I'm going to do is I'm just going to draw in some left side rectangles just to kind of see what left side rectangles look like in these cases. So left side rectangles here would be an underestimate. Okay. Left side rectangles here, also an underestimate. Interesting. So maybe it doesn't depend on concavity at all, because all it changed there was concavity. Left side rectangles here, too much, right? It's too high. Left side rectangles here, also too much. So it looks like it only depends on increasing and decreasing. So it's not going to depend on concavity at all. Okay. So this is, again, another thing I would not memorize, right? I would always draw a picture. Just draw a picture to figure it out. A picture. And you just have to remember, either you have to remember that it depends on increasing, decreasing, or you can draw this chart every time and say, oh, it looks like it only matters if it's going up or down. Okay, so, but in general, if you have left side LRAM, so LRAM, remember, so if we have something that's increasing, then it's going to be an underestimate because we're missing all that area, right? If it's something that's increasing, then, sorry, increasing what I just did. If it's decreasing, something like this, it's going to be an overestimate, right? So we're just looking at whether we're getting too much area or not enough. RAM is exactly the opposite. If we have something that's increasing, RAM is going to be an overestimate. And if we have something that's decreasing, RAM is going to be an underestimate. Okay, so question is, can we get approximations, right? Because we have all these gaps going on. We have all these gaps, and this question is, can we get a better approximation, and can we actually be perfect? So our goal, remember, our goal is to get this area, right? Exactly what's underneath the curve. And you might have already figured this out. If I want to get a better approximation, I could just use more rectangles, right? So like in this parabola that we've been dealing with, if you use, let's say, a right side approximation, if you only use 4, like we did initially, there's a lot of gaps, right? But if you were to go to using more, so if you have lots of rectangles, what happens is those overestimates get a lot smaller. Right here we have all of this overestimate, right? These are a lot smaller. So the more rectangles that you have, certainly the better. So more rectangles, more rectangles will definitely get you a closer approximation. So then the question is, how does it get perfect? Well, how many rectangles do you think I would want to use? If I could use an infinite number of rectangles, that would be perfect. Okay, so infinite number of rectangles. That sounds like it's going to involve some kind of a limit, and we'll talk about that in 5.2. Okay, in 5.2, we'll talk about if you had an infinite number of rectangles, how would you actually find what that area would be, right? How wide would each rectangle be then? Well, each rectangle would just like be like the width, thickness of a line. Right? There would be no overlap, and those lines would end up completely filling in the area, and you would be able to find the area under that curve. So we'll talk about that in 5.2. So now would be a good time to try that worksheet. The worksheet does a nice job kind of for the beginning of it, kind of taking you through this exploration that we really just talked about. But the problems they have there's an MRAM, there's an RRAM, and an LRAM. They're really good. So if you want to try it on your own, you can. I'm just going to kind of talk through the solutions here. So if you want to pause the video, you can. Otherwise, you can just follow along with me. So here's the MRAM, and this solution's on line 2. So what's going on here is we go from 0 to 3 seconds, and we go up to 9. We go up to 9 here on our x squared, right? Because 3, 9 would be on the point on the curve here. So 3, 9. Right, so what I do here is I write the width of each rectangle to find the area. So we get the width of each one is going to be 0.5. The height is going to depend on the midpoint, right? The midpoint of each rectangle. So the first midpoint would be at 0.25. So I do 0.25 squared, and then multiply them together to get my area. The next one, halfway between 0.5 and 1 would be 0.75. So 0.75 squared times 0.5 is 0.28125. Halfway between 1 and 1.5 would be 1.25, then here's 1.75, and here's 2.25, and then 2.75. I'm just plugging those in because if I plug them into the function, that's going to give me the height of this rectangle, right? That height there would be f of 2.7, because this is 2.75 down here. Okay, and then you multiply that height by the width of the rectangle, and then you add all those areas together. That looks very close to 9. Okay, so it's very close to the value of 9. So maybe 9 is the exact area. I don't know. right? But it's not going to be perfect because the overlap and the missing parts don't perfectly line up, right? So it's not going to be quite perfect. Next, we have left hand. Left hand should be too small, right? Left hand should be too small. Notice it's a lot smaller than our MRAM was. It's a decreasing function. So LRAM is an increasing function, so it should be an underestimate. So an over approximation would be something that's a decreasing function, right? Because I'm going to be getting too much. Jump over my numbers here again. 0.5 this time I'm using the left-hand side. So the first rectangle has no height at all, right? The next rectangle is going to be whatever f of 0.5 is, then f of 1, f of 1.5, f of 2, f of 2.5. And that's the last one that I use because we're only stopping at 3. Add all those rectangle areas together, get 0.875. Last one is the right-hand approximation. So the right-hand approximation, this time you can see it's going to be definitely an overestimate, right? Because our right-hand rectangles go over the top too far. The first one we have too much area right here. And then we use the value at 1, and then the value at 1.5, and the value at 2, value at 2.5. This time we do use the value of 3. Notice that we're doing right hand or left hand. You don't use one of the endpoints, right? In this case, I didn't use 0 at all. The other one, the left hand, I didn't use 3 at all. So 0.5 width for each one of those, multiplied by the height, which is determined by the corner touching the function here. Square all those, multiply by the 0.5, add them together, gets 11.375. Notice that's too much. Last one was not quite enough. And then this 8.375, I'm telling you right now, the area under there is 9. That's really close. Okay, it's not great, but it's close. If I wanted to make it better, more rectangles, right? All right. I got here for 5.1. I should be able to try the homework doing left and right side Riemann approximations. See you in 5.2. Love you guys. That's why I'm here. Have a great day.